Okay. Good evening to one and all who is going to see this video. My name is Sai Kumar. I am working as an assistant professor with the RMD Engineering College in the Department of Tripoli. I am currently pursuing my PhD with Anna University in the area of processor microarchitecture. The name of the channel what I have created for posting the videos associated with your processor architecture is Processor Architecture Design. To start with, the first video will be dealing about what do the expressions associated with the digital logic gate actually convey, and how we are going to use those expressions, the meanings associated with those expressions in creating a microprocessor oriented circuit. So the very purpose of starting this channel is to create a sense of creativity, the people who are going to watch this channel, and also to create their own microprocessor circuits that will be suiting to their needs as well as to the application they want to design it. I expect all of you, the viewers who are going to see this video, to kindly subscribe my channel as well as click on the bell icon as well as put a like so that it will be provided as an encouragement for me for posting so many videos which will be very useful for designing a microprocessor circuit of your choice. With this basic introduction, let me go into my presentation. So today we are going to see about inner meaning of logic gates. There are totally 7 gates over here: NOR, NAND, NOT, AND, OR, XOR, XNOR. So the first gate which we are going to see is called as NOR gate. A NOR gate is nothing but a zero detector. So why do we call this as a zero detector? Now let us see. This is the basic symbol that we use for a NOR gate. It consists of totally 2 variables, namely A and B, and one output variable Y. This table to the right hand side of the symbol gives the truth table of a NOR gate. The expression for the NOR gate is nothing but given by De Morgan's theorem. The complement of a sum is nothing but equivalent to product of the complements. This is theoretical part. But what do we actually understand from this expression? Both the variables must not be occurring. So how do I confirm this? Whenever I am providing a bar, as you might have come across in your digital logic circuit, we will be representing a variable in 2 forms. One is a complemented form, another one is uncomplemented form. Complemented form means we will be putting a horizontal bar over a variable or a star over the particular variable. When we are not providing any of these things over a particular variable, we indicate them to be a uncomplemented form. So over here, I have provided horizontal bar over the 2 variables over here. One is A, another one is B. So whenever I am providing a bar over a variable, it indicates logic 0. That means that particular variable has not occurred. So here, since there are bars over the 2 variables, this indicates both the variables should not occur. So a NOR gate provides an output of 1 only when the 2 variables are not occurring or when both the variables are 0. So since it has this behavior, it is also called as a zero detector. Suppose there are variables, input variables, n-bit input variables provided to a digital logic circuit, and if I want to find whether a 0 has occurred at the input, I have to go with a NOR gate. The next gate which we'll be seeing in our sequence is NAND gate. So again, the expression for a NAND gate is given by this is the symbol for the NAND gate, and this is the truth table associated with a NAND gate, and this is the expression associated with a NAND gate. The expression associated with a NAND gate is given by De Morgan's theorem. De Morgan's theorem for a NAND gate is nothing but complement of your product is nothing but equivalent to sum of the complement. This is theoretical. Now we'll go to the expanded form of the expression, which is nothing but a bar dot b bar plus a bar dot b plus a dot b bar. So a bar dot b bar, it indicates both the variable has not occurred. A bar dot b indicates only b has occurred. A dot b bar indicates only a has occurred. So this is the meaning of the NAND gate. So a NAND gate provides an output of 1 when none of the variables occur or when one of the variables occur. So this is the basic inner meaning of the expression associated with a NAND gate. The next gate which we are going to see is OR gate, which is having a behavior exactly opposite to the behavior of NAND gate. So here the expression for a OR gate is nothing but A or B. The plus symbol indicates a OR operation, and the expanded expression for a OR gate is given by A bar dot B plus A dot B bar plus A dot B. So A bar dot B, it indicates only B has occurred. A dot B bar indicates only A has occurred. A dot B indicates both the variables has occurred. Previously in NAND gate, what we did? Either none of the variables must occur or one of the variables must occur. But in case of your OR gate, either one of the variables must occur or both the variables must occur. Okay. So A dot B, what does it indicate? That we'll be seeing it in the upcoming slide. So as far as the OR gate is concerned, either one of the variables must occur or both the variables must occur. That too, when both the variables are occurring, it must be following a sequence. Anything before a dot, all these are AND expressions. A bar dot B, A dot B bar, A dot B, all these are AND expressions. So this dot, any variable before the dot must be occurring first, any variable after the dot must be occurring second. So this is the inherent meaning associated with the AND operation, which we will be seeing in this slide. Any variable before the dot operator must be occurring first, any variable after the dot operator must be occurring second. Since the AND gate provides an output of 1 only when both the inputs are 1, the AND gate is also called as a one detector circuit. Suppose I am having an n-bit input variable, and if I need to detect whether all the bits are equivalent to 1, I automatically go to AND gate. So what do this expression convey? It indicates A and B should occur, but with a small sequence to be followed. What is the sequence? First A must occur, then B must occur. Next gate, NOT gate. It indicates a variable has not occurred. So here in this case the variable is A. When the variable is 0, the output of the NOT gate is equivalent to 1. That means whenever a bar is provided over a variable, it indicates a logic 0. Logic 0 means the variable has not occurred. Next one, XOR gate. So XOR gate, this is the symbol associated with the XOR gate operation. And now we are going to see what is the expression A bar dot B plus A dot B bar. A bar dot B indicates B alone has occurred. A dot B bar indicates A alone has occurred. So now what is the difference? Why we call this as XOR gate? It is nothing but exclusive OR gate. So what is the thing it is excluding? For this, we need to just look into the truth table of OR gate. Here, in a OR gate, the output is equivalent to 1 when one of the inputs is 1 or when both the inputs is 1. 0, 1, 1. 1, 0, 1. 1, 1, 1. So for OR gate, the output is equivalent to 1 when one of the variables occur or when both the variables occur. Whereas now we just need to look into the truth table of XOR gate. 0, 1, 1. 1, 0, 1. 1 1 0. This condition is being excluded from the OR gate. In a OR gate, when both the inputs are 1, the output is 1. Whereas in XOR gate, when both the inputs are 1, the output is 0. Since this particular condition associated with a OR gate is excluded, this derived gate is called as exclusive OR gate. So what does the meaning of the expression convey? Either B alone must occur or A alone must occur. Only when both the inputs are different from each other will I be getting the output from the XOR gate. XNOR gate. Here, this is the right hand side is the truth table and this is the expression. This is the symbol associated with the XNOR gate. Let me look into the expression. The expression for XNOR gate is A bar dot B bar or plus A dot B. A bar dot B bar indicates none of the variable has occurred. A dot B indicates both the variable has occurred. Now let us just go into the truth table of NOR gate. So in a NOR gate, when both the inputs are equivalent to 0, output is 1. When both the inputs are high, the output is low. Now we'll come to the XNOR gate. Here what do we see? In XNOR gate, the last condition is being inverted. For a NOR gate, when both the inputs are high, the output is low. Whereas in a XNOR gate, that output condition is high. That means it has been inverted. So the condition which is present in a NOR gate has been excluded. It has been converted into 1. So that is the meaning for exclusive NOR gate. So from the expression we can conclude a combination of NOR gate and AND gate will be giving me the XNOR gate. This is theoretical part. But what is the inner meaning? A bar dot B bar means both the variable should not occur. A dot B means both the variable must occur. Either both the variables must not occur or both the variables should occur. So these are the meanings of the various logic gates. Let me look into the further meanings of these expressions. A bar indicates the variable A has not occurred. B bar indicates the variable B has not occurred. That means these two things are logic 0. A dot B bar indicates A alone has occurred. Second meaning is A is greater than B. This is called variable age deduction logic. That means A is elder than B. Next one, a 0 should occur only after a 1 has occurred. If I am having a bits are coming 1, 0, 1 like this, if I am going to give it to the expression A dot B bar, then the value 0 must occur only after a 1 has occurred. Okay, first 1 must occur, then only it must be followed by a 0. That is the meaning of A dot B bar. Similarly, A bar dot B. B alone has occurred. This is the first meaning. A is lesser than B or A is younger than B. Variable age deduction logic. It is telling what is the age associated with a variable, whether it is greater, whether it is younger, or whether it is elder. Third meaning, a 1 must occur only after a 0 has occurred. This is the meaning for A bar dot B. Next expression, A dot B. This indicates B must occur only after A. This is one meaning. Already a 1 must have occurred, then only the next one in the data sequence is allowed to occur. Suppose there are data sequence 1, 0, 1, 1 like this. In that sequence, a 1 must have already occurred, then only the next one is allowed to occur. That is the meaning of A dot B. Next one, A bar dot B bar. Again, if the sequence of data bits, a 0 must occur. First, already a 0 must have occurred. Then only the next 0 in the sequence is allowed to occur. This is one meaning. Or both the variables does not occur. These are the two meanings. You have to use these meanings according to the context of designing the microprocessor circuit. A or B. What is the meaning? One should occur only after a zero has occurred. That is A bar dot B. First a zero must occur, then a one must occur. Second meaning, a zero should occur only after a one has occurred. A dot B bar. Third meaning, a one should occur only after previous one has occurred. That means first a one must be occurred, then only the next one in the sequence is allowed to occur. Either one of the variables must occur or both the variables must occur. Next one is A bar plus B bar, which is nothing but the expression for the NAND gate. Here what is the meaning? Here a 1 should occur only after a 0 has occurred. A bar dot B. A 0 should occur only after a 1 has occurred. A dot B bar. A 0 should occur only after a previous 0 has already occurred. That means if there are a sequence of data bits, first a 0 should occur, next only the next 0 is allowed to occur in a sequence. So with this video, I have provided you the basic information associated with the expressions of the logic gate. In the next class, we will be seeing how do we implement these logic gates in Model Sim software as well as in Xilinx ISE software. Thank you for today's session.